All right, let's get right into it. We've got a paper today that's really making some waves. It's called Token Shuffle, towards high-resolution image generation with autoregressive models.
Yeah, this one's pretty interesting.
The big headline. They're getting autoregressive models, the LLM-style ones, to do state-of-the-art text-to-image at a massive 2048 by 2048 resolution.
Which is huge. And they're saying it even beats some diffusion models on certain benchmarks.
Right, exactly, and with better efficiency. The core idea is this thing they call token shuffle. It cuts down the number of visual tokens the transformer needs to chew on for these really high-res images.
Clever. How does it do that?
Yeah.
Leveraging redundancy.
Precisely. Dimensional redundancy in the visual vocabularies. They have these two operations. Token shuffle to merge local tokens, and then token unshuffle to put them back.
Okay.
And the result, they're like 2.7 billion parameter model. It hit a 0.77 score on the hard prompts in GenAI benchmark.
Wow. Okay, that's better than Lamigan.
An LDM, yeah. Plus, human evils apparently preferred it for text alignment, visual appearance, fewer visual flaws, too, in some comparisons.
Okay, so this could be pretty significant for AR models in the image space.
Definitely. So today we're going to dive deep into how token shuffle actually works and, what it might mean going forward.
Sounds good. It's tackling a problem that's been around for a while, right? AR models for images. They've struggled with scaling.
Yeah, that success they've had in language hasn't quite translated smoothly to high-res images.
It's the tokens. Just way too many tokens needed for detailed pictures.
Creates this huge computational bottleneck. It's why diffusion models kind of took over the high-res scene.
Yeah, they sidestepped that specific issue. So this paper is offering a potential way back for AR models.
A pretty clever way, it seems, this token shuffle idea.
It really hinges on that observation about the visual tokens maybe not needing all that embedding space they get in the MLLMs.
Right. So let's break down token shuffle itself. You mentioned the two parts.
Yeah, token shuffle and token unshuffle. Think of token shuffle as grouping nearby tokens together, spatially local ones.
Merging them, yeah.
Then the transformer does its thing on these merged tokens, and afterwards, token unshuffle unpacks them, puts them back in their original spatial spot.
Giving you the high-res detail back.
Exactly. And the scores you mentioned, that 0.77 on GenAI Bench.
Yeah, for a 2.7B model.
That really shows it's working. It's not just a theoretical gain, it's beating established models. And the human evils preferring it for text alignment and appearance. That's key.
So the potential impact here. Maybe AR models have a stronger future in high-res image gen than we thought. A more efficient path, perhaps.
Could be. It definitely warrants a closer look at the mechanics. How does it really work under the hood?
Okay, let's set the stage a bit. Why is this even a problem? I mean, applying the next token prediction idea from LLMs to images. It sounds appealing, right? A unified approach.
Oh, absolutely. The dream is one model that just gets text and images seamlessly. And when you think about representing images for these models, it basically boils down to two camps: continuous visual tokens or discrete ones.
And this paper, like others, leans towards discrete.
Yeah, they mention EMU3, Chameleon. Big models tend to favor discrete tokens.
Why is that? For folks maybe less deep in the weeds here.
It mostly comes down to integration with the LLM architecture. Discrete tokens are conceptually simpler to handle. You just treat them like extra words in the vocabulary.
It's expanding the token set.
Exactly. Continuous tokens often mean you need different model parts, different loss functions, maybe fiddling with the attention masking. It gets more complex.
Right.
Plus, the paper makes a point that it's not totally clear yet if continuous methods don't negatively impact the text side of the MLLM. So discrete tokens often win out for simplicity and keeping that cross-modal performance strong.
Makes sense. Stick with what works for the language side. But then, boom, the high-resolution problem hits.
That's the trade-off. Discrete tokens are easy to integrate, but hard to scale for images.
Because you just need so many.
An enormous number.
Yeah.
210, 24 by 13024 image, they mention, might need like 4,000 visual tokens.
Okay.
And transformers, their compute cost scales quadratically with that sequence length. So 4,000 tokens. I think it's really expensive, really fast for training and for just generating an image.
So convenient architecture, but a scaling nightmare for pixels. Meanwhile, diffusion models.
Diffusion models have been crushing it on high res. They don't have that same kind of discrete token count limitation because they operate differently, more in a continuous space.
So while people are working on making LLMs handle longer sequences better.
Yeah, things like sparse attention, different architectures.
Those are often big changes, maybe focus more on text anyway. So a direct fix for AR image generation at high res using standard MLLMs and discrete tokens. That was kind of the missing piece.
Precisely. It was a critical gap.
Which brings us to their core insight, this visual dimensional redundancy. Okay, unpack that. What's redundant?
Okay, so think about how you get visual tokens into an LLM. You usually use something like a VQGAN, right?
Right, a visual tokenizer.
And that VQGAN might create codes, say, in a 256-dimensional space. That's enough to reconstruct the image pretty well.
Optimized for the visual task.
Exactly. But then you take those 256-dimension codes and you embed them into the LLM space. And that space might be, what, 372 dimensions? 4096? Much bigger.
Ah, okay. So the visual information is suddenly sitting in this massive vector space.
Right. And the authors argue, essentially, that a lot of that extra dimensionality isn't really being used effectively for the visual information. It's redundant for the visual part.
Like putting a golf ball in a shoebox. It doesn't need all that room.
That's a perfect analogy. And they tested this. They took a 2.7B llama model, used linear layers to squish the visual embedding dimension down, and then expand it back up.
Compressing it.
Yeah, trying different compression factors. And figure 3 shows they could compress it by up to 8 times, 8x, with almost no hit to the image generation quality.
Wow, 8x compression. That really drives home the point about redundancy. They did say pushing it further started to hurt, though.
Correct, there's a limit. But that 8x finding is key. It shows there's fat to trim, so to speak, in how visual tokens are represented dimensionally within the MLLM.
Okay, so they found the fat. Now, how does Token Shuffle trim it to reduce the number of tokens, not just the dimension?
Right, because reducing the number of tokens is what really tackles that quadratic scaling cost. Token Shuffle is designed as this plug-and-play module pair.
Plug and play sounds good. Easy to add.
That's the idea. And they took inspiration from Pixel Shuffle, which you see in super resolution.
How does that work, the Pixel Shuffle analogy?
Pixel Shuffle rearranges pixels from different channels of a low-res feature map to make a higher-res map with fewer channels. Token Shuffle is similar in spirit. The Token Shuffle part takes a small grid of neighboring visual tokens, say S by S tokens.
It's like a little patch of the image representation.
Exactly. And it merges them together. It basically combines their information into a single fused token, primarily along the channel dimension.
So instead of the transformer seeing, say, 4 tokens in a 2x2 patch, it sees just one fused token.
Precisely. But before merging, there's a crucial step. They use a shared NLP layer to compress the dimension of each original token in that patch, from dimension D down to D divided by squared.
Ah, so they shrink the dimension first to make room for the merge, so the final fused token isn't enormous.
Right, it keeps the overall dimensionality in check. But the big win is that the number of tokens the transformer sees is reduced by that factor of squared for that patch.
That's the sequence length reduction. If S2, you cut the tokens by 4x locally. Huge.
Massive impact on computation. Then, after those fused tokens go through the main transformer blocks,
The heavy lifting part.
yeah, the token unshuffle operation comes in. It takes those fused tokens and unpacks them, disentangling them back into the original SXS grid of local tokens.
Putting the spatial detail back.
Exactly. And again, there's an MLP layer involved, this time to expand the dimension back up from DS on to the original D.
So it's like compress locally for efficiency in the transformer, then decompress back to full granularity.
That's a great way to think about it. They also add some residual MLP blocks in both shuffle and unshuffle, just to help with feature fusion refinement. A couple of linear layers with GEOU, standard stuff.
Okay, but it's important, they say, this reduction only happens during the transformer computation, right? Not the whole pipeline.
Key distinction, yes. The VQGAN still outputs the original number of tokens, and the final prediction step probably operates on the unshuffled tokens too. The savings purely within those expensive transformer layers.
But that's where the bottleneck is.
That's where it matters most. And this lets the model effectively predict a whole group of local tokens in one autoregressive step, instead of predicting every single tiny token one by one. That's how it speeds up high-res generation.
Figure 4 apparently shows this really well. The efficiency gains.
Yeah, it illustrates the quadratic gains.
Yeah.
With S2, you see roughly a 4x drop in FLOPs and the token count processed by the transformer. Pretty significant.
Okay, mechanism makes sense. How did they actually build this? What model, what tokenizer?
So the base is a decoder-only transformer, a llama variant, standard autoregressive setup.
Okay.
For the visual side, they used a pre-trained VQGNN, looks like the same one from llama again. It downsamples the image by 16x and has a vocabulary of 16,384 discrete visual tokens.
And they just mix those tokens in with the text tokens.
Yep, concatenate the vocabularies. They add special tokens, start of image and end of image, to signal the image part of the sequence. Training is just standard next token prediction across everything, text and image tokens.
Pretty standard MLLM recipe so far. But the training for 2048 by 2048, that must have been tricky. How did they stage it?
It was a 3-stage process. First, train at 512 to the 512 without token shuffle. Resolution's low enough there. Sequence length isn't killing them yet.
Get the basics down.
Right. Then, stage 2, scale up to 1024 by 1024 and introduce token shuffle with S2.
Okay, bringing in the efficiency trick.
Exactly. And finally, stage 3, push to 2048 by 2048, starting from the 1024 model, still using token shuffle. They mentioned needing more training tokens at each stage, too, naturally.
But they ran into trouble at 2048, right? Instability.
They did. Said the loss in gradients would suddenly spike after a while. Tried the usual fixes, lowering the learning rate, weighting the visual token loss more heavily. Didn't work. Neither of those solved the instability.
So what did work for that crazy resolution?
They started looking at logit scale issues, something people see in training, really huge LLMs. They tried QK norm in the attention layers and also adding a Z-loss term to the objective function.
QK norm helps normalize attention scores. Z-loss penalizes large logits.
Right. QK norm helped a bit, but the instability still came back eventually. The key turned out to be adding the Z-loss. The combination of QK norm and Z-loss finally let them train stably at 2048 by 2048. They used a pretty small weight for the Z-loss, like 1E5.
Interesting that Z-loss helped even on a 2.7b model for this task. Usually you hear about it for like 100b plus models.
Yeah, that's a neat finding. Might be particularly relevant for stabilizing these very high-resolution image generation tasks, regardless of model size.
Any quirks in how they run inference? Generating the images?
A couple practical things. First, they stick that start of image token onto the end of the text prompt.
Why? Just to be sure it starts making an image?
Exactly. Otherwise, the model might just keep generating text sometimes. It forces the transition.
Okay.
Second, they mentioned that sometimes, especially earlier in training, the model might output a weird mix of text and image tokens. So during inference, once that start of image token appears, they force the model to only sample from the visual vocabulary afterwards.
Prevents garbled outputs. Makes sense.
Ensures you get a clean image sequence.
Now, they also use Classifier free guidance, CFG. That's common in diffusion. How did they adapt it here for AR?
They do use it. Train time, they randomly drop the text prompt 10% of the time. Inference, they adjust logits using the guidance scale, alpha. Standard CFG mechanics.
But they thought vanilla CFG might not be ideal here.
Yeah, they had a specific concern for autoregressive models. When you do the unconditional generation prompt dropped, the model always starts predicting the first image tokens based on the same initial system tokens.
Right. The context is identical at the very start.
So the unconditional logits for those very first few visual tokens are always the same. Quite consistent.
Okay.
And their worry was if you just subtract those fixed unconditional logits from the conditional ones right at the start, you might introduce weird artifacts that then get amplified as the generation continues sequence by sequence.
Because the AR process builds on previous steps, earlier artifacts could propagate.
Exactly. Unlike diffusion, where the whole thing is refined more globally. So they proposed a new CFG scheduler just for inference.
What's the goal?
To basically reduce or even zero out the CFG effect for the very first few visual tokens. Let the model get started cleanly, then ramp up the guidance.
Let the later tokens handle the alignment push.
Right. They tried a bunch of scheduling functions, linear, half linear, drop first, sine, sigmoid. Figure 5 shows the comparisons.
And which one won?
They settled on the half linear scheduler as the default. Said it gave the best results visually and based on feedback.
Seems like a thoughtful adaptation for the AR setting. Okay, let's talk numbers. How did it actually perform on benchmarks?
They used GenEval and GenAI Bench. For GenAI Bench, the main metric was VQA score, uses a VQA model to check semantic alignment between the prompt and the image.
Better than just FID or CA score for this kind of text guidance.
They argue it is, yeah, more nuanced.
Right.
And because their training captions were maybe shorter, like Llamagan's, they reported scores using original prompts and prompts rewritten by Llama 3 to be longer, just for consistency.
Fair enough. So the big result on GenAI Bench.
Table 1 shows it. Their 2.7b token shuffle model gets a VQA score of 0.77 on the hard prompts.
0.77. How does that stack up?
Pretty impressively. It beat Llamagan, the pure AR comparison, by 0.18 points. That's a big jump. And it even beat LDM, the diffusion model, by 0.15 points on that VQA score metric.
Whoa, okay. Beating LDM on semantic alignment? That's strong. It suggests token shuffle isn't just efficient, it's genuinely improving the quality for AR models.
Seems that way based on VQA score. And the results on GenEvol, shown in Table 2, were also promising. Competitive with other AR and even some AR plus diffusion hybrid models, shows good general quality beyond just resolution.
Numbers look good, but image generation.
Yeah.
You gotta see it right. How did humans rate the outputs?
They did extensive human evaluations too, using GenAI Bench prompts. Compared token shuffle against Llamagen, Lumina MGPT, another MLLM, and LDM.
What were people looking for?
3 things. Text alignment, does the image match the prompt? Visual flaws, any weird artifacts or glitches?
Yeah.
And just overall visual appearance, does it look good?
I'm the verdict.
Figure 6 lays it out. Token shuffle was consistently preferred over both Llamagen and Lumina MGPT on all 3 criteria.
Okay. Better than other MLMNR approaches. How about against LDM, the diffusion model?
That was interesting. Token shuffle scored comparably, maybe even a bit better than LDM on text alignment and visual appearance.
Really? Okay.
LDM was rated as having slightly fewer visual flaws.
Ah, that visual flaw thing again. Seems like a persistent challenge for AR methods, maybe. We should come back to that.
Definitely. But first, they also have visual examples in Figure 7. Side-by-side comparisons with LDM, Pixart LCM, Llamagen.
And what do those show, qualitatively?
Visually, token shuffle seems to stick closer to the text prompts than Llamagen, and obviously hits much higher resolution for similar cost. It looks pretty competitive with the diffusion outputs, too, based on those examples.
Seeing is believing sometimes. Okay, so to really nail down why token shuffle works, they must have done ablations, right? Picked it apart.
Oh yeah, quite a few.
Yeah.
They looked at the design choices within token shuffle itself. First, the number of MLP blocks in the unshuffle parts. They tried 4 or 6 instead of the default 2.
Any benefit?
Figure 9a suggests, not really. Training loss didn't improve significantly, so 2 blocks seemed sufficient.
Balance. What else?
They compared shuffling versus just dropping tokens like in the SXS window, just keeping 1 token and throwing the rest away.
That sounds lossy.
And it was. Figure 9b shows performance tanked. So retaining and merging the information from all tokens in the window is crucial.
Makes sense. You need that local context. Did adding extra position information help, like local coordinates within the window?
They tried adding extra positional embeddings, local and global. Figure 9c shows no real benefit.
Why not?
They think the MLPs in Token Shuffle already capture local position implicitly,
right,
and the main transformer already uses row P for global position. So adding more explicit position stuff was redundant.
Okay, the existing parts handled position well enough. Any other alternative designs they tested?
They tried using a resampler thing, like in the SeedX model, and also a super simple version, just concatenating features and using basic MLPs. Figure 9D shows both were worse than their main Token Shuffle design. So their specific way of doing the local fusion and disentanglement seems important.
Good validation. What about the shuffle size itself? That's S value. Did they test different sizes?
Yep. Figures 10 and 8 cover experiments with S1, which is basically no shuffling, just the MLPs. S2, their default, and S4.
What's the trade-off?
As you'd expect, bigger S means more token reduction, so better efficiency. But it also led to slightly higher training loss and maybe a little bit of blurring in the final images, figure 8.
So more aggressive shuffling saves more compute, but might cost a tiny bit of quality.
Potentially, yeah. They found S1 and S2 gave excellent quality, with S2 offering that nice 4x token reduction. S2 seemed like the sweet spot.
Got it. Now, they also compared this whole shuffle idea to just using a better VQGAN from the start, one that compresses more.
Yes, that's a really important comparison in the appendix, section B.4. It's the obvious alternative. Instead of shuffling tokens from an 8x compression VQGN, why not just use a VQGN that compresses by 16x directly?
Right, simpler approach.
So they compared token shuffle, using the 8-pipe VQGN plus S2 shuffle, against a model using just a 16x compression VQGN. First, Table 3 shows the 16x VQGN reconstructs images much worse than the 8x one, more lossy.
Okay, higher compression hurts reconstruction. Does it hurt final generation too?
Seems so. Table 4, VQA score, and Figure 18, Human Evil, both show that the token shuffle approach generated better images than the model using the high compression 16x VQGN, even though the compute cost was roughly similar.
Interesting. So strategically shuffling tokens from a decent VQGN is better than just using a VQGN that brutally compresses everything up front.
That's their conclusion. Token shuffle gives better results and also more flexibility, since you can tune the shuffle size to trade off quality and efficiency.
They didn't mention some caveats about that comparison being perfectly fair, though.
Yeah, small print.
Yeah.
The VQGNs weren't trained identically, slight dataset differences, but they felt the main conclusion holds. Token shuffle seems superior to just relying on extreme VQGN compression.
Okay, that makes a strong case for their method. Now let's loop back to those visual flaws we mentioned earlier. The human evil showed LDM was slightly better there.
Right. And the paper addresses this directly in the discussion. They suggest it's likely not due to token shuffle itself or the VQGN losing info. It's more a general characteristic of autoregressive models.
Why is that?
Because of the causal masking and the sequential next token prediction nature. It limits the model's ability to enforce global consistency easily. One slightly off prediction early on can sometimes cascade.
The error propagation issue.
Exactly. While token shuffle adds some local interaction, it doesn't fundamentally change that autoregressive process.
Yeah.
They point to things like randomized autoregressive generation, RAR, as a possible future direction to maybe improve global consistency in AR models.
So token shuffle is a big step, but maybe not the final word on fixing all AR image generation quirks.
Yeah.
Fair enough. What about limitations in future work they mentioned?
Main things were, this work used a 2.7B model. Scaling it up to larger LLMs like 7B or 30B is the obvious next step. See if the benefits hold or even increase.
Makes sense.
And also, they want to support flexible resolutions and aspect ratios, not just fixed sizes like 2048 by 2048, more like what EMU3 can do.
All right, let's try and wrap this deep dive up. For our listeners, the technical folks out there, what's the big takeaway from token shuffle?
I think it's that token shuffle offers a really practical, seemingly effective way around that token count bottleneck for AR models doing high-res images. It makes them competitive again.
Yeah, and the way it exploits that dimensional redundancy is pretty neat. Plus, being plug and play is a big plus for actually using it.
Definitely. And the result, holding their own against and even beating diffusion models on metrics like VQA score, that's impressive. It suggests AR has real potential here.
It feels like it could be a building block, right? A core design element for future efficient high-res MLLMs.
Could be. It's a smart way to handle the data characteristics.
So, maybe a final thought for everyone listening. Token shuffle worked well for images by exploiting redundancy and manipulating tokens. Where else could we apply similar ideas? What other data types or tasks in these big multimodal models have inherent redundancies we could exploit with clever token manipulation for better efficiency or performance?
That's a great question. Video, audio, maybe even complex structured data. Thinking about modality-specific token processing beyond just simple embedding. That seems like a really fruitful area.
Finding those smart compression or manipulation strategies will be key as these models get bigger and handle more data types.
Absolutely. Token shuffle is a really cool example of that kind of thinking.
Well said. It's definitely an exciting space to watch, and token shuffle adds a really interesting twist to the AR versus diffusion story for images. Thanks for digging into this one today.
My pleasure. It was a fascinating paper.